today we're going to talk about rotational motion. So far we've talked about linear motion and then Newton's laws and gravity. But there's a special type of physics that we'll have to look at when we're talking about how things move, if they rotate or if they move in circular motions. So this will be rotational, circular, and orbital motion. So the reason we care about this for astronomy is the planets in the solar system are rotating, stars rotate, and then things that are in orbit, especially the planets in our solar system, are almost in circular orbits. So the physics that we talk about for circular motion, we can apply to those objects. So to review the gravity stuff that we talked about last time, the potential energy or gravity, and this symbol means proportional to. So this just means the potential energy is proportional to or goes as 1 over r. The force of gravity goes as 1 over r squared, and the tidal force goes as 1 over r cubed. So the tidal force dissipates faster than the regular gravitational force, and potential energy dissipates the slowest of any of them. We've talked about two different equations for gravity. So we had the lowercase g gravity and the uppercase g gravity. So when did we say those two equations should be equal? Yeah, so these are equal near the surface of the Earth. So if you look at the equation, if you set the m1 to be the mass of the Earth and r to be the radius of the Earth, and you plug all those in, then you'll get the mass of whatever object times 9.8 meters per second squared. So planets orbiting the sun, we've talked about how those motions are elliptical orbits, but they're very, very close to being circular orbits. And it turns out the physics for things moving in a circle is a lot easier to understand than something moving in an ellipse. And so we'll approximate all of their orbits to be circular orbits. Okay, so this diagram, we're putting the sun at the center of this red circle, and the red circle is the path that a given planet is orbiting the sun. Let's say this is the path of the Earth orbiting the sun. At each of these points with a blue and a green arrow, what's being shown is the velocity of the planet at that point, and then the acceleration that is acting on that object. So this acceleration is causing the object to move in a circle, and so that is a special type of acceleration called centripetal acceleration. And for things that are moving in a circle, the centripetal acceleration is equal to the velocity of that object squared divided by the radius of the circle. And the centripetal acceleration always points towards the center of the circle, no matter what point you're looking at. And the velocity is always tangential to the circle, meaning it points kind of basically perpendicular to the centripetal acceleration. So the power of this centripetal acceleration, so first we can put that centripetal acceleration into Newton's second law, so multiply centripetal acceleration times the mass of the object. So if we're using the Earth as the orbiting body, then this lowercase m would be the mass of the Earth. And now we use the relationship between centripetal acceleration, the tangential velocity, and r, and we replace that in our Newton's second law equation. And now, I guess I kind of skipped a step here, but what we're doing is we are, so I guess conceptually, what force is acting on the Earth to make it orbit the sun? Gravity. So this centripetal force has to equal the force of gravity. So that's why on the left side I've replaced the centripetal force with the gravitational force that Newton came up with. So now we have an equation where there's force of gravity on one side, and then there's mass times velocity squared over the radius of the orbit on the other side. We can simplify that equation a little bit, so the mass of the Earth cancels on both sides. That was little m, and so it turns out the mass of the orbiting body doesn't matter. And then the r in the denominator on the right side can cancel with one of the r's in the denominator on the left side. And so now we have this relationship between velocity squared, g, which is the constant, Newtonian gravitational constant, m is the mass of the sun, and r is the radius of the orbit. And so we'll put that in a box, and we'll come back to that later, and we'll use it in the future. So the big takeaway here is just that things that go in circular orbits have centripetal acceleration. So that's just an acceleration that points towards the center of the circle that makes them do the circular motion. There are two vocab words that sound similar and are both related to rotations, but they are different things. So centripetal is not the same thing as centrifugal. So centripetal force is the thing that makes something do circular motion, whereas centrifugal force is a consequence of something that is rotating. So basically, centripetal forces cause rotations, and centrifugal force is a force something feels as it is rotating. So one of them is a cause of rotation, and one of them is an effect of rotation. So we've already seen gravity is an example of centripetal acceleration, and then if you had a ball on a string that you were spinning around above your head, the tension on that string would be a centripetal acceleration. What a centrifugal force is so if you've ever been driving in a car, probably as the passenger, and the driver turns the wheel really sharply, you feel like you're being pushed towards the outside of the car. So what's really happening is this is a consequence of inertia. So you were traveling in the car, and let's say the car was going straight. Now the driver turned the wheel of the car, so the car wants to start going to the left, but your body isn't attached to the wheel of the car, so your body wanted to keep going straight. So your body wanted to keep going straight, but now the car is going to the left, so you feel like you're being pushed out the right window of the car. So centrifugal force is just a consequence of being in something that is turning or rotating. And so there's a video here that might help.
Moving in a circular path, the net force is called a centripetal force or center-seeking force. And if the rope is cut, the can will no longer maintain a circular path, and it will fly in a straight line tangent due to Newton's first law of inertia. The centripetal force is the force that creates the tension on the string the center seeking force. There are two perspectives in this example, outside of the can and inside the can. As Newton's third law states, for every action, there is an equal and opposite reaction. From outside of the can, there should be an outward reaction force to the centripetal force. This center fleeing force is known as the centrifugal force. The reactive...
So the big takeaway here, so from the perspective of the bug inside of the can, they're not attached to the string, so the string is what's making the can rotate in a circle. The bug is not attached to the string, it's just standing inside of the can. And so the bug feels like it's being pushed towards the outside of the can, which is the centrifugal force. So you can only get the centrifugal force if you have something that's rotating. And it's a consequence of the rotation, whereas the centripetal force is the cause of the rotation. So one centripetal cause, centrifugal is the effect of the rotation. So this is maybe a refresher, or maybe this is new from geometry. When we talk about things that move in circular motion, in physics, we will typically use the unit of radians. So when we measure angles, if we go from the right side of the circle all the way around the circle and do one complete loop, that would be 360 degrees. If you do half the circle, you get 180 degrees. So radians are just a different way of measuring those same angles. So all the way around the circle is equal to 2 pi radians. Halfway around the circle would be pi radians. And there's this other diagram on the right that shows you the conversions between different angles and their radian equivalent. But the easy way to convert between radians and degrees is to just use this conversion of 360 equals 2 pi radians, or 180 equals pi radians. And it's basically just that the math that we're doing works with radians, but it doesn't work with degrees. So if we remember when we talked about position, velocity, and acceleration, that was where something is in space, how fast it's moving through space, and how fast that velocity is changing with time. We'll have a set of similar properties for things that are moving in circles or spinning. So we'll have theta, which is the angular position. We'll have omega, which is the angular velocity, or how fast its angle is changing. And then we'll have alpha, which is the angular acceleration, which is how fast the angular velocity is changing. And the arrows on everything is just telling you that those are vector quantities. So what the rules we learned for vectors apply to things that are moving in rotational motion. And for angles, we'll use the units radians. For angular velocity, it's radians per second. And angular acceleration is radians per second squared. And there's an easy way to convert between the linear version. So in this representation, S is a linear distance. And if you want to convert the linear distance to an angular distance, you just divide the linear distance by the radius of the circle that it's going around. So let's see that as an example. So we just said the angle to go all the way around the circle was 2 pi radians. So we have this equation that relates theta, an arc length, or a distance, and the radius of the circle. So the circle has a radius r. And we just said that the angle to go around, all the way around the circle was 2 pi radians. So what is the distance to go all the way around the circle? So that, this line that I just drew is the length s. So if we want to solve for s, it's just theta times r. We said theta was 2 pi radians. And so the distance to go all the way around the circle is 2 pi r. So this 2 pi r should look familiar to what you learned in geometry, right? You learned the perimeter of a circle is 2 pi times its radius. So where that equation came from is this relationship between angle and distance and radius. So that was an easy example, but you could do more complicated things, like what if I wanted to know the arc length for this angle theta? So if you didn't know this equation, you might try to like set up a right triangle and then try to approximate what this arc length would be. But using this formula, it's pretty simple. I just take whatever angle this is in radians, multiply it by the radius, and that would be the length of this arc of the circle. And then there's a similar conversion between the angular velocity and the linear velocity, and the angular acceleration and the linear acceleration. You just have to use the radius of the circle to convert between the linear and the angular terms. So just like there was a relationship between position, velocity, and acceleration, there's relationships between angular acceleration, and angular velocity. So the angular velocity is just the rate of change of the angular position. So take the change in angle, divide it by the change in time, and you'll get the angular velocity. So remember, the triangle is the Greek letter delta, and that just means to take the final minus the initial. And then same thing for angular acceleration. Angular acceleration is the change in angular velocity over change in time. There are two different types of frequency in physics, and it's important to pay attention to which one they're talking about. So angular frequency is the same thing as the angular velocity, but that's different than just frequency. So the angular frequency is 2 pi times the frequency. So frequency you might have heard, if you have heard like the refresh rate on a screen, that'll be given in hertz, and that frequency is just a measure of how many times something happens per second. So if your screen refreshes 100 times per second, that would be a frequency of 100 hertz. So this frequency is different than the angular frequency that goes into all of your equations, but it's really easy to convert between the two. You just have to pay attention to this factor of 2 pi. So let's do some practice converting between the refresh rate for your screen of 120 hertz. What will that angle be, or the angular frequency be? And you can just round to the nearest 10. Okay, so this is the equation that we need for converting between angular frequency and frequency. We're given the frequency is 120. Pi, I'll just say that's about 3 to make the math easy to do in my head. So now we have 6 times 120. And so that's about 720 radians per second. And the closest choice is 750 radians per second. So then, just like we had kinematics equations for linear motion, we also have kinematic equations for angular motion. So these rotational kinematic equations relate, so the first one, the final angular velocity is equal to the initial angular velocity plus angular acceleration times time. The second one, the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the change in angle. And then the last one, the change in angle, is equal to the initial angular velocity times time plus 1/2 times the angular acceleration times the time squared. So these equations will let you know how fast something is spinning at some time in the future and how much it has rotated during some period of rotation. So let's do some examples. So if you have a not solid state hard drive in your computer, then the way that the hard drive works is by spinning very quickly. So the hard drive can start from rest and reach a frequency of 120 hertz in 20 seconds. So we're going to calculate the angular acceleration of that hard drive and how many degrees did the hard drive rotate through in that 20-second time frame. So let me write down all of those kinematic equations. And now I will make my chart of variables. And so this is what we have to fill in. They tell us that something starts from rest, so that means that its initial angular acceleration is 0, or angular velocity is 0. And then eventually it reaches a frequency of 120 hertz. So they're giving us something that's close to angular velocity, but instead they're giving it to us as a frequency. So they gave us this frequency, and we just saw how to convert 120 hertz into angular velocity. So we used this equation, and we got about 720 radians per second. So that's what we'll put here. They're asking us to find the angular acceleration, so we don't know that yet. And then the second question is asking for how many degrees did the hard drive rotate through, so we don't know the angle yet either. But they do tell us that this motion happens over the course of 20 seconds, so that goes in our time variable. So given these variables, which one of these equations do we want to pick to solve for the angular acceleration? Yeah, the first one. So the last one, we don't know what the change in angle is, so we can't use that one. Same with the second one, we don't know the change in angle. So all that's left is the first equation. So we want the alpha by itself, but I know that the initial angular velocity is 0, so I'll just cancel that out. Then to get the alpha by itself, I just need to divide t to the other side. Now I can plug in my numbers. So 720 divided by 20. Like 36. No, it can't be 36, can it? Yeah. Something like 36 radians per second squared. Okay, so then we can come in here and fill in our angular velocity or angular acceleration. And now we're on to the last question. How many degrees did the hard drive rotate through? So we want delta theta. So which equation do you guys want to use? Yeah, so we've got most people saying 3. So 3 is probably the easiest to use because the delta theta is already by itself. But you could also use the second equation if you wanted to. So I'm going to do that here. So delta theta equals omega initial plus 1/2 alpha t squared. Omega initial times time. The initial angular velocity is still 0, so the first term just goes away. Now we can just plug in our numbers since delta theta is by itself, and that's what we want. So we have 1/2 times 36 times 20 squared. So 20 squared is 400. Divide that by 2 would be 200. times 36 would be like 7,200. And now what units is that going to have? And is that the final answer that we care about? So let's practice what units that should have. So we know the final answer should be 7,200 somethings, but we don't know what those somethings are. So the units for the 36 are radians per second squared. And the units for time are in seconds, but then we squared it, so this unit would be seconds squared. So when you multiply these together, the second squared in the bottom cancels with the second squared on the top, and the units that you're left with are radians. So this answer was 7,200 radians. But the question asked us how many degrees did the hard drive rotate through, not how many radians. So now we have to take the 7,200 and convert it to degrees. So this is where we use that conversion factor. There are 2 pi radians in 360 degrees. So we would divide 7,200 by 2 pi, and then multiply it by 360. That is not something I think I can do in my head, but we have the answers on the next slide. When we are talking about things that are rotating, what shape they are and what axis they're rotating about matters. So if we're thinking about a planet orbiting a sun, we could just approximate it to being a point source that's doing circular motion around the star, which would be at the center of this blue arrow. But if we want to think about the planet rotating on its own axis, we can't just pretend that it's a point source anymore, and we instead have to realize that it's a spherical shape. And so this I is the moment of inertia, and you can think about this as how easy or hard it is to make something rotate. So the Earth is more or less a solid sphere, and so you would use this moment of inertia 2/5 mr squared. And so this is just a value that you can multiply by the angular velocity, for example, or the angular acceleration, and we'll see some consequences of that in a second. If the Earth was hollow, it would have a different moment of inertia, and so it would actually be harder to make it start rotating, or harder to make it stop rotating. And that's because all of the mass would be concentrated along the edge, and it's harder to stop all of that mass from rotating if it's not distributed throughout the whole object. So how the mass is distributed and the shape that it's distributed in can change the moment of inertia. And then also the axis of rotation can change the moment of inertia. So if you take this rod and you rotate it about a point on its center, then it is very easy to rotate it. But if you instead try to rotate the rod about a point on the end of the rod, it becomes much harder to rotate. So 1/3 is a bigger fraction than 1/12, and so this rod rotating about the edge is harder to rotate than a rod rotating about its center. So this gives you an idea for how hard it will be to make something start rotating, based on its shape, the distribution of the mass, and what axis you're trying to rotate it about. We've already talked a little bit about angular momentum when we talked about Kepler's laws and Newton's reformulation of Kepler's laws. And we said that you could get angular momentum just by taking the linear momentum and multiplying it by r, like the radius of some circle. And it turns out there's another way of thinking about that, and that's using the moment of inertia and the angular velocity. So another way to think about the moment of inertia, I, is that it's analogous to mass for linear motion. So you can think about mass as how hard is it for me to make something start moving linearly, and you can think of moment of inertia as how hard it is to make something start moving rotationally. So we talked about forces, and there's going to be a rotational equivalent to force called torque. It's the Greek letter tau. And again, we can get that by just taking the linear version force, multiplying it by r, like the radius of a circle, or we can take the angular acceleration and multiply it by the moment of inertia. Because remember, force is mass times linear acceleration. So if we take the rotational version of acceleration, which is angular acceleration, and we take the angular version of mass, which is moment of inertia, multiply them together, we'll get the angular version of force, which is torque. We talked about energy and how there's kinetic energy and potential energies. Things that are rotating are a certain type of kinetic energy called rotational kinetic energy. And the formula for rotational kinetic energy is 1/2 moment of inertia times angular velocity squared. And so if something is moving and rotating, then it will have linear and rotational kinetic energies, and you can add those two things together. If we remember back to when we introduced angular velocity, we said we could equate angular velocity to linear velocity divided by the radius of the orbit or circle that the object is moving in. So if we make that substitution, we'll see that both sets of equations have the linear velocity term in it now. So we can factor out that linear velocity, and we're left with mass plus moment of inertia divided by r squared. And we're going to use this in a moment to simplify some equations that we're going to introduce. Now, if something is in an orbit, so the moon is orbiting the Earth, or the Earth is orbiting the sun, there will be some total amount of energy that the object has as it's orbiting. There's kinetic energy and potential energy. The kinetic energy we'll write as 1/2 mv squared. And if we remember from very beginning of lecture when we talked about centripetal acceleration, we came up with this relationship between the velocity of the Earth going around the sun and the mass of the sun the radius of Earth's orbit, and g, which is the constant. So let's plug that back into this equation for kinetic energy. And when we do that, you'll notice that both of these terms look the same. One has a negative in front, and the other one has a 1/2 in front. And so this consequence of centripetal acceleration and forces allows us to simplify the whole orbital energy of a planet or a moon or a satellite down to this one simple equation. So the total energy just depends on a constant, the mass of the planet that the object is orbiting, or the sun, the mass of the orbiting object, and then the radius of its orbit. And the fact that this energy is negative is just telling you that this is a bound orbit. So a satellite going around the Earth is not going to escape from Earth's orbit, and so this negative sign tells you that it's basically stuck orbiting that object. We can also see how Newton made changes to Kepler's third law now that we've talked a little bit about the physics of rotational motion. So if we start from that red box that we derived from centripetal acceleration, and we realize that, so we'll assume that the planets are orbiting in circular motion, then the velocity of that orbital motion is going to be the distance that they travel, which is just the circumference of a circle, divided by the period of that orbit. Right? So I'm just doing velocity equals distance divided by time. Now I'm going to square both sides of this equation so I can plug it in for this velocity on the right-hand side. So that's the setup, and the rest is just algebra to get the equation in a form that looks familiar. So we get p squared on one side and distance cubed on the other side, which is exactly what Kepler came up with for his laws. And this is how Newton came up with the modification to Kepler's laws. So you just need a little bit of understanding of rotational motion, and then a little bit of clever substitution and algebra, and you can get the same results. And so that brings us to the final way that you can change something's orbit. So we talked about there's some orbital friction between the Earth and the Moon due to tidal forces, so that's one way to change an orbit. You can accidentally venture too close to, say, Jupiter if you're a comet, and that can change your orbit. Or, more importantly, for things that humans like to launch into space, like rocket ships, we can just use our thrusters to increase or decrease our velocity, and that can change our orbit. So this is one of the ways you can transfer from, say, orbiting the Earth to orbiting around the Moon, or orbiting around a different planet. Okay, so that's kind of it for today. We learned that for every linear term, there's an analogous rotational form. Just like there's linear kinematic equations, there's rotational kinematic equations. And then using that understanding of rotational motion, we could see where some equations will simplify and how Newton was able to derive some improvements to Kepler's laws.